All right, welcome back. Dr. P here, and in this lecture, which will be the last one for Chapter 19, we'll look at conjugate addition. Now, what is conjugate addition? Well, let's take a look at the following molecule here. This is a conjugated aldehyde or ketone. So depending on what R groups I might have here. I'm not going to draw those R groups in, but these could be a variety of different things. Okay. We also refer to this as an alpha beta unsaturated aldehyde slash ketone. So if I had a hydrogen there, I'd have an alpha beta unsaturated aldehyde. If I had some alkyl group there, it would be an alpha beta unsaturated ketone. Let me just label these here because that's our alpha carbon, like we talked about, and that's our beta carbon. Now let's go ahead and take a look at some resonance structures here. Why am I doing this? Well, I want to show you guys why these alpha beta unsaturated species react a little bit differently than regular aldehydes and ketones. And also they react differently than just a regular alkene. All right, so I have a partial negative charge on this oxygen, sorry, and a partial positive charge, not a partial, a full charge. In this resonance structure, I have a full negative charge on the oxygen and a full positive charge on that carbon. And that's what we're used to seeing, right? Well, with the presence of another double bond here, because it's conjugated, I can draw another resonance structure. And in this other resonance structure, my oxygen still has a negative charge, but now I have a positive charge on my beta carbon there. So this is essentially what we're looking at is the following. We have that bond is polar, but it turns out that this guy is also somewhat polar too. So we get partial negative charge there, partial positive charge there, and a partial positive charge there. So we do have electron density pulled this way as well. And again, this is our alpha carbon and our beta carbon. Okay, so what this means is now we've got two sites of electrophilic carbon. So we potentially have two places that we could get addition. We have the regular carbonyl carbon, and then we have the conjugate, the beta carbon. So for example, we could have something like a Grignard, which is going to be a direct addition, sometimes called a 1,2 addition. And so my Grignard, so let's just take my simplest case here. We'll take that guy there, and we will react it with CH3MgBr, and then H3O+, and we will get H. CH3OH. However, our conjugate addition, which will work with a different reagent, the Gilman reagent, and this is also called a 1,4 addition. When you think about it, we're adding, for example, the 1,2 addition, we're adding, but ultimately a hydrogen on carbon, or on the oxygen, 1, and then 2 is on the carbon. 1, 4 would be adding 1, and 2, 3, 4. So what we actually get then instead is the following. So we'll treat this with a Gilman reagent. So in this case, CH3 2 CuLi. And I believe I talked about this way back in 12A, just a little bit as another nucleophile. This has the interesting property of it adds preferentially at the beta carbon. So we'll quench that with H2O. And our net result, even though we're adding, we do add a hydrogen to protonate things, it just ends up protonating in a slightly different place. So we actually have this guy essentially stays intact, our carbonyl carbon here. Now, why does that happen? Well, let's go ahead and take a look at the mechanism. First of all, let me just mention, to make the Gilman reagent, we would take 2 equivalents of some alkyl lithium. We'll go ahead and react that with copper iodide, copper 1 iodide, and we'll get R2CuLi plus Li, lithium iodide. So that's just a byproduct salt, and this here, of course, is our, and it's just going to add, one of they're going to be symmetric. We're going to have these Gilman reagents are always symmetric, and they're just adding one of the methyl groups. All right, so what does this look like mechanism-wise? Well, let's look at the general mechanism. Okay, so let's go ahead and let's just take the following ketone. And we will take some kind of nucleophile. So this could be our Gilman reagent. It could be something else. It could be an oxygen nucleophile. It could be a nitrogen nucleophile. And we get attack on the beta carbon. The electrons from that double bond get pushed up to the next bond over. And in turn, we get the electrons on the carbon-oxygen double bond pushed up onto the oxygen. So that now gives us the following. And this guy here can then, if we have some, proton source, so H+, in the case of the Gilman, it's our water, our water serves as a proton source. So it's not H+, but it's H from water. And now we can have, we could protonate here, but we could also get that, and we'll regenerate our carbonyl there. This guy will get picked up and go on that. This proton will get picked up and go on that carbon. And there we go. Okay, so you could protonate at the oxygen here, and that actually gives you what would be called an enol. instead of the keto species, and we'll talk about that in chapter 22. But just understand that this is why when we're doing the when we're doing this conjugate addition here, this is why we keep the ketone at the end here. So yeah, we add our nucleophile and then we protonate, but we end up protonating at the alpha carbon instead of on the oxygen. Okay, and this is the mechanism for it. All right. So some examples. Let's look at maybe some examples here. We could have I'll just set that aside there. So some examples. We could, of course, have the Gilman reagents, so the organocopper reagents, and we could have, say, oxygen. We could also have nitrogen, which is probably most interesting. And so let's say we had, this is the example from the text, let's say we had 2-cyclohexenone, and we treat this with CH3NH2, and what we'll end up getting is O minus, double bond there, and then N HHCH3, positive charge there. And subsequent proton transfer is then going to give us now this guy here. So a typical amine would be something that would add at the beta carbon. So there are a variety of nucleophiles that will add preferentially at one versus the other. So one important thing to remember is actually the Grignard adds directly, the Gilman adds at the conjugate, the beta carbon. So I would say that's one of the take-home messages here. So if you're looking to do some sort of synthesis or something using a conjugate addition, make sure you're using the right reagents. All right. So we'll talk more about some conjugate addition with some other types of nucleophiles in chapter 23, actually. But this wraps up chapter 19, and we can talk more about stuff in person when we meet in person. All right. Well, stay safe out there, everyone. I will see you later. Bye now.